Welcome to lecture 6 of Business Intelligence and Management Support Systems. So today we are going to look at Online Analytical Processing, which is also known as OLAP. We spent the past few weeks building up our understanding of how data is structured and moved, and we learned about data models, star schemas, and ETL pipelines, which showed how data is structured and moved. And today we are going to bring all that together and look at how analysts actually query and explore a data warehouse once it is ready. By the end of this lesson, you should be able to explain what OLAP is and why organizations use it. Then distinguish between the two main types of OLAP systems. Understand how data is represented as a multidimensional cube and confidently apply the 5 core OLAP operations both conceptually and through SQL queries. Before we begin, let's first of all see where OLAP fits within everything we have already covered. Now, try to remember lesson 3 and lesson 4 and lesson 5. We started with source systems where raw data, which were sitting in operational databases or data lakes, was there, right, in source systems. Then we looked at how ETL and ELT pipelines extract that data, clean it, and load it into a data warehouse that is structured using a star or snowflake schema. That data warehouse is now full of well-organized, clean, historical data ready for analysis. Now, OLAP is what happens next. This is the analytical layer that sits on top of the data warehouse and allows business users, analysts, and managers to slice through that data, explore trends, and answer complex business questions. This is done all without needing to understand the technical details underneath. So remember, fact tables store our measurable events like sales quantities and revenue figures. Dimension tables give context to those facts by telling us who bought something, where the sale happened, and when. The star and snowflake schemas organize these tables into a structured, optimized for query. The ETL and ELT pipeline is what moved all that data into the warehouse. Then OLAP sits at the top of this entire chain, providing the interactive analytical capability. OLAP stands for Online Analytical Processing. The word online here does not mean the internet. Basically, it means interactive and real time. When an analyst uses an OLAP system, they are not submitting a query and waiting hours for a result. They are asking a question. They get an answer almost instantly and then ask for the next. It can be a more refined question. So this is a conventional way of exploring data. This concept was formally defined by Dr. Edgar Cott, who many of you may know as the person who invented the relational database model. He described OLAP as a technology that uses a multidimensional view of aggregate data to provide quick access to strategic information for the purposes of advanced analysis. A simpler way to remember this is this acronym FASMI, Fast Analysis of Shared Multidimensional Information. This captures the same idea: speed, multiple dimensions, and shared access across an organization. You really have to remember this. OLAP is not a storage technology. It does not replace your data warehouse. It is the query and analysis layer that sits on top of the warehouse and gives analysts a powerful, flexible way to explore the data that has already been prepared and stored here. Let's take time to explain one of the most important slides in our lesson. On the left, you can see that we have a structure that students who remember lesson 3 should recognize this immediately. This is a fact table called sales fact. It has 3 foreign key columns: date ID, which links to a time dimension, product ID, which links to a product dimension, and location ID, which links to a location dimension. It also has 2 measure columns, units sold and revenue. These are the things we actually want to analyze. Now, what OLAP does is take those 3 foreign keys and treat each one as an axis in 3-dimensional space. Look at the cube in the right side. Time becomes one axis. Product becomes a second axis. Then location becomes the third axis. The result is a cube. We have 3 axes. Precisely, we can call this a data cube. Each point inside the cube represents a unique combination of time, product, and location. And the value stored at that point is the measure, such as the units sold, or it can be the revenue. So this is a fundamentally different way of thinking about data compared to a flat relational table. Instead of rows and columns, we think in terms of dimensions and cells. Each cell in the cube answers a very specific question. How many units of this product were sold in this location during this time period? Also, MOLAP. MOLAP systems pre-compute this entire queue and store it in a specialized multidimensional database. ROLAP systems do not build this physical queue. Instead, they compute the equivalent results on demand by running SQL queries against the relational star schema. So both achieve the same analytical outcome, just through different mechanisms. We will come back to MOLAP and ROLAP in more detail. Let's now see why multidimensional analysis is so powerful through a concrete example. Now imagine a company's sales are up for this quarter. That is great news, right? But it immediately raises some follow-up questions. Which region is responsible for the increase? Once we identify the region, which specific store within that region is driving the growth? And once we identify the store, which product category is contributing the most to those results? Each of these questions zooms in on the data from a single angle. It can be geography, then store, then product. This chain of increasingly specific questions is exactly the kind of analytical workflow that OLAP is designed to support. The analyst can move from one question to the next fluidly without needing to write a new database query each time. The key insight here is plain SQL can absolutely answer any one of these questions. But if you want to explore interactively, ask one question, see the answer, ask a follow-up, pivot to a different view, then writing SQL each time like this is cumbersome. OLAP tools provide a structured vocabulary of operations that let analysts navigate dimensions interactively. We are going to learn that vocabulary today, and it consists of 5 operations: slice, dice, drill down, roll up, and pivot. There are two main architectural approaches to building an OLAP system, and they differ in a fundamental way. When do they do the computational work? That is how they differ from each other. MOLAP, multidimensional OLAP. This does the work upfront. When data is loaded into the system, it pre-computes all the possible aggregations and stores them in a specialized multidimensional cube structure. This means that when a user asks a question, the answer is essentially already there. It just needs to be retrieved. The result is very fast query performance. However, there are trade-offs. Because the cube is pre-built, it can only contain data that was included when the cube was last processed. There is no real-time connection to the source data. If new data arrives, the cube must be rebuilt, which can take a significant amount of time. The query language used to interrogate a MOLAP cube, that is, interact with a MOLAP cube is called MDX, which stands for multidimensional expressions. MOLAP is also less scalable than ROLAP because the cube can only hold a finite amount of summarized data. Now let's look at ROLAP or relational OLAP. This takes the opposite approach. It does not pre-compute anything. Instead, it works directly against the relational tables in the data warehouse, using SQL queries to compute results on demand. This means it can handle very large volumes of data. It always reflects the current state of the data warehouse, and it is highly scalable. The trade-off is that queries are slower because the database must do all the computation at the time the question is asked rather than having the answer pre-calculated. So despite these differences, both MOLAP and ROLAP serve the fundamental analytical purpose. The choice between them depends on the organization's priorities: speed versus volume, freshness versus performance. So this comparison between ROLAP and MOLAP summarizes the differences between the two. We are going to summarize across 7 key dimensions. First one, data structure. ROLAP stores data in relational tables, the same rows and columns and foreign key relationships we have already studied. MOLAP stores data in a hierarchical cube structure where dimensions nest within each other. On data volume, ROLAP can store enormous amounts of data because it leverages the full capacity of a relational database. MOLAP is more limited because it only stores pre-summarized aggregated data. The row's transactional detail is not kept in the queue. Real-time access. With ROLAP, the moment new data is loaded into the data warehouse, it is immediately available for analysis. But with MOLAP, there is a lag because the cube must be rebuilt before new data is reflected in query results. On query speed, MOLAP wins here because all aggregations are pre-computed. ROLAP queries can be slower, particularly for complex aggregations over large datasets because the database must compute the answer from scratch each time. Query language. ROLAP uses standard SQL, which most data professionals already know. MOLAP uses MDX, multidimensional expressions. This is a specialized language designed specifically for querying multidimensional cube structures. We will see a brief example of MDX later in today's lesson. So think of it this way. If your organization prioritizes real-time dashboards on massive data sets, then ROLAP will be the right choice. If your priority is lightning fast query response on a well-defined manageable data set, then MOLAP delivers that. For the remainder of today's lesson, we are going to use a single consistent example to demonstrate all OLAP operations we are going to learn. This example involves a printer company selling 4 product types: monolaser, inkjet, photo, and portable printers across 5 US states: Colorado, Washington, Arizona, Utah, and California, over the course of the year 2017. So this cube on the left has 3 axes, as I just showed you. The vertical axis is going upward at the back. It shows the location, the 5 states. The horizontal axis going to the right side represents product, which are the 4 printer types. And the axis going into the page, this one, it represents the time. So each layer of the cube corresponds to a single day in year 2017. So the cube has, as a whole, contains an entry for every combination of state, product, and day throughout the entire year. The table on the right shows what a single layer of that cube looks like. Specifically, the layer for the 1st of January 2017. The numbers in each cell here are units sold. For example, California sold 80 monolaser printers on that day and 110 inkjet printers. Colorado sold 85 photo printers, which was the highest single cell value for that day. So keep this example in mind. Every OLAP operation we discuss from this point forward will be applied to this cube. There are 5 fundamental operations in OLAP, and they form the vocabulary. You can call it the vocabulary that analysts use to explore a data cube. You can think of them as 5 different ways of looking at the same data. So let's look at each of them in detail. The slice operation is the most straightforward of the 5. We take our 3-dimensional cube and fix one of its dimensions to a single value, which will remove that dimension and give us a 2-dimensional table. So in this example, we are slicing the cube on the time dimension, and we are going to fix it to 1st of January 2017. What we get as a result is what you see in this table: location as rows and product as columns. And the units sold are as the cell values. Time has been eliminated from the equation. We are now looking at a flat 2-dimensional snapshot for that single day across all locations and products. There is also a variant of the slice operation called the slice summarize variation. So instead of fixing time to a single value and dropping it, we collapse the time dimension by summing across all its members. So rather than seeing one specific day, we can see totals that are aggregated over the entire year. The location by timetable mentioned here is not like that. It's not the variant, right? It's the original slice operation. So the key conceptual point is this: slice reduces the cube by one dimension. You can start with 3 dimensions and then you will end up with 2 dimensions. This is the slice summarize variation. The location by timetable here that you can see at the bottom of the slide demonstrates the slice summarize variation. Each row is a state, each column is a date, and the final column, it shows the total annual sales for that state across all products. The dice operation is often confused with slice. Let's make sure that we know precisely about the difference. Slice fixes a dimension to exactly one value and removes that dimension entirely. Dice, on the other hand, filters a dimension to a subset of its members while keeping that dimension in the result. Look at the example. We start with the location by product table we produced from the 1st January 2017 slice. You can see that all 5 states are visible. When we apply a dice operation to filter the location dimension to only 3 states, Utah, Arizona, and Colorado, we remove California and Washington from the result. But we still have a location dimension in our output. It just now has 3 members instead of 5. The product dimension is unchanged. Notice in the 2 tables on the slide that the data for Utah, Arizona, and Colorado is identical in both. The dice operation does not change the values. It only restricts the scope. So in practice, dice and slice are often chained together. An analyst might first slice to a specific time period to get a 2-dimensional view, then apply a dice to further narrow down the locations or products of interest before moving to a drill down or roll up. Drill down and roll up are navigation operators. Rather than filtering or slicing the cube, they move us up or down a hierarchy within a single dimension. Dimensions in OLAP are often structured hierarchically. For example, you can see the location dimension might be organized as country, then state, then region, then individual dealership. There is a hierarchy. Each level is more granular than the first one above it. It has more details. When we drill down, we move from a less granular level to a more granular one. In the table here, we start at the state level where Utah shows a total of 40 monolaser printers sold. When we drill down into Utah, we break that 40 into its component cities. Salt Lake City accounts for 20, Park City for 5, and Ogden for 15. These 3 numbers add up to 40. This confirms that the drill down has correctly disaggregated the state total into city level detail. There is more granularity when you drill down. Roll-up is simply the reverse. If we are already looking at city level data and we want to go back to seeing state totals, we just roll up, which means aggregating the individual city values back into their parent state. The result is the same state level row we started with. So it's important to understand the constraint. How far can you drill down? This is limited by the dimension table. If the location dimension table in your data warehouse only contains a state column and a country column, then you can drill down from country to state, but no further. You cannot drill to city if the city column does not exist in the dimension table. The pivot operation. This operation is maybe the most intuitive to understand, but sometimes the hardest to visualize. It rearranges which dimensions appear on which axis of the result without changing a single data value. Think of this as rotating the table so that what was across the columns is now down the rows and vice versa. So in this table, in the before table, we have location running down the rows and time running across columns. The values are total sales figures. For example, California had 275 total units sold on the 1st of January and 670 units sold on the 2nd of January, with a full year total of 16,250. After the pivot seen here, the axes have been swapped. Time now runs down the rows and location runs across columns. California still has 275 on the 1st of January, 670 on the 2nd. The numbers are identical, but the orientation of the table has changed completely. Why would an analyst want to do this? You might have this question. This is purely about readability and preference. A manager who wants to scan how a particular city performed over time would prefer time as rows, reading downward. A manager who wants to compare multiple cities on the same date would prefer time as columns. The pivot operation supports both needs without duplicating or altering the underlying data. Now we are going to look at how each OLAP operation is expressed as an SQL query against our star schema. We are going to use the same printer sales scenario. There will be 5 queries across this slide and the next, one for each OLAP operation. Let's look at the first one. This query implements the slice operation. We are fixing the time dimension to a single value, 1st of January 2017. It is asking total sales by product for 1st of January 2017. Basically, what total units were sold for each product on that day. Select specifies the 2 columns we want in the output, the product name and the sum of units sold. The sum function adds up all the unit values for each product. From sales, fact tells the database to start with the central fact table, where all sales events are recorded. The letter F is just a short alias. Join time dimension connects the fact table to the time dimension table So we can filter by a human readable data rather than by a numeric ID. Join product dimension connects the product dimension table so we can display product names rather than just product ID numbers. The where clause. This is the slice. It restricts the result to only rows where the date is 1st January 2017. Every other day is excluded. Group by. Groups the filtered rows by product. So we get one output row per product rather than one row per individual sale. Order by. This sorts the output with the highest selling product at the top. Let's look at the second query. This query implements the dice operation. We are keeping 2 dimensions active, location and product. But we are filtering the location dimension to only 3 of the 5 states, which is exactly what dice does. Select. We now want 3 columns, the state name, the product name, and the total units. Join. We join the location dimension so we can filter by state name and display it in the output. Where? This is the dice. The in keyword filters the location dimension to a subset of members, 3 states out of 5. This is different from the slice where clause. Where equals clause because in selects multiple values, not just one. Here we selected only one value, but in selects multiple values. Group by. Here we group by both state and product name. This gives us one row per state product combination in the output. For example, Utah monolaser, Utah inkjet, Arizona monolaser, and so on. Let's look at the third query, ROLAP. This query implements the ROLAP operation on the time dimension. The fact table stores data at the daily level. One row per sale event per day. By asking SQL to group by month and year rather than by individual date, we are rolling up the daily detail into monthly summary totals. Here the sum function adds together all the daily unit values that fall within the same month and year combination, producing a single monthly total. Join. The time dimension table contains not just the date, but also derived columns like month, number, and year, which we can use for grouping at higher levels of the hierarchy. Group by. This is the roll-up. By grouping at the month and year level rather than the date level, we collapse all the individual daily rows into one aggregated row per month. If the data contains 365 daily rows for a given product and location, this group by would reduce them to 12 monthly rows. Order by. This sorts the output chronologically, so the time series reads naturally from January through December. Let's continue with the final 2 OLAP operations, drill down and pivot. Both of these have more complex SQL queries than the previous three. This query in question 4 implements the drill down operation. We start at the state level. So the question is, break Utah's state total into city level detail. So we start at the state level, scope to Utah, and then navigate down to the city level within that state. This is equivalent to expanding a row in a report to see its breakdown. Where close? We first scope the query to a single state. Think of this as the context for the drill down. We are not interested in all states. We are only interested in Utah. This is similar to first slicing to a specific location before drilling into it. The group by, this is the drill down. By adding the city column alongside state in the group by, we are asking the database to break the aggregation down one level further in the location hierarchy. Rather than one row for Utah, we now get one row per city within Utah. The sum function then adds up all the unit values for each city. Order by sort cities from highest to lowest sales, making it easy to immediately identify the top performing city within the state. Let's look at the final query, pivot. Here, we try to show each product type as a separate column. This query implements the pivot operation. Without pivoting, product names would appear as row values. You would get one row per state product combination. The pivot transforms those row values into separate columns, giving you one row per state with 4 columns of product data side by side. This is a much more readable format for comparison. The key mechanism is the case when expression inside each sum function. Let us walk through the first one carefully. Sum case when product name equals monolaser, then units sold end as mono. Case when expression reads every row in the fact table one by one. For each row, it asks, is the product name for this row equal to monolaser? If the answer is yes, it contributes that row's units sold value to the sum. If the answer is no, the case when returns a null, which sum simply ignores. The result is a column called mono that contains the total monolaser units sold and nothing else. Each of the 4 case when blocks does exactly the same thing, but for a different product type. The group by. This one, group by on state, the query produces one output row per state. Within each state row, the 4 case when sums each independently accumulate their respective product totals. The final result is a table with 5 rows, 1 per state, and 4 product columns, 1 per product type. This is the pivot. Now we will bring together the SQL query patterns we have just seen and map each one to its corresponding OLAP operation. We will also introduce MDX for those who want to work with MOLAP systems in future. So this is basically like a reference guide. Slice corresponds to where clause with an equals condition. This fixes one dimension to exactly one value. Dice corresponds to where with an in clause, filtering to a subset of values. ROLAP corresponds to a group by at a higher causal level of a hierarchy, such as grouping by month instead of day. Drill down corresponds to a group by that includes a finer level of the hierarchy, such as adding city alongside state. And pivot corresponds to conditional aggregation using case when expressions or the native pivot keyword where supported. So it is worth that noting that some database systems such as SQL Server and the Oracle have a native pivot keyword that achieves the pivot operation more cleanly rather than using case when expression. However, the case when approach works in virtually every SQL database and makes the underlying logic completely transparent. Here, you see an MDX example, how you query a pre-built cube directly. This is the query language used in MOLAP systems. MDX looks quite different from SQL. Rather than specifying tables and joins, you describe the result in terms of cube axis. So select, you can see the select clause in MDX defines what appears on each axis of the result grid. Here, all members of the product category level are placed as columns. On rows, similarly, all members of the location state level are placed as rows. This defines the two visible dimensions of the result. The from clause. Instead of naming a relational table, we name the cube itself. The cube already knows about all its dimensions and their hierarchies. The where clause in MDX acts as the slicer. It fixes the time dimension to 1st January 2017, equivalent to what the SQL where clause did in query 1, if you remember. This is the OLAP slice operation expressed in MDX. So what you can conclude from what you see here is very simple. ROLAP uses similar SQL against your star schema tables. MOLAP uses MDX against a pre-built cube. The analytical questions being answered are identical. Only the underlying engine and the syntax differ. This final summary table consolidates everything into a single reference you can use for revision. The slice operator, the purpose is to focus on a single value of one dimension. The operation fixes that dimension to one specific value and produces a two-dimensional result. In SQL, this is a where column equals value condition. Dice, the purpose is to focus on a subset of dimension members. The operation filters one or more dimensions to multiple values. In SQL, this is a where column in with a list of values. The purpose of drill down is to obtain more granular detail about a dimension. The operation navigates from a coarser level of a hierarchy to a finer one. In SQL, this is achieved by adding a finer grained column to the group by clause. The purpose of ROLAP is to summarize detail into a higher level view. The operation navigates from a fine level to a coarser one. In SQL, this is achieved by removing fine-grained columns from the group by clause and letting the sum function aggregate upward. Pivot. The purpose is to present the same data in a different orientation. The operation rearranges the dimensions without changing any values. In SQL, this is achieved using case-when expressions to transpose row values into separate columns. The most important takeaway from today's lecture is captured here. The 5 operations are not separate, disconnected tools. They are vocabulary, a shared language that analysts use to navigate and explore multidimensional data. In a real analytical session, an analyst would typically chain several of these operations together. For example, slice to a particular time period, dice to a relevant set of locations, drill down into city level detail, roll up to monthly summaries, and finally pivot the result into a format suitable for a management report. So, mastering this vocabulary means being able to ask and answer complex business questions quickly and systematically.